which are really disjoint of each other. They share in the sense that they share in two properties. One, that they are both dealing with large deviations as a mathematical tool to get where we want. And two, that they are both dealing with things which you can think are connected to statistical physics type questions and random graphs, or graphs, maybe not even random. Part one is what I planned originally to do in lecture 2, and will kind of be supplement to what we will do later, maybe in lecture 5. It is taken from my Saver paper with Andrea Montanari. It is section 113 in the beginning of this survey, and I will just essentially go over the essence of this piece of the survey. But it is well-known classical material that was known way before we wrote the survey, both in physics for sure, many years ago, and in mathematics as well. Part two is this nonlinear large deviation. It's a follow-up of some works of, or connected to some earlier works of Chatterjee alone and with Varadan. And this specifics was taken from the paper, joint paper we wrote that just appeared in Advances of Mathematics. There is the account that I will give you is equivalent to the account that is given in section 10 of Chatterjee's recent survey paper in the archive, which skips all the technical actual calculation. And I will also skip all the actual calculation. It will be the same, really. But if you want the difference, is this section 10 is really cut and paste from our paper, but without the stuff. So let me first do part one. So the Curie-Weiss model is really the easing on the complete graph on N. Okay? So we are looking at this particular measure, and what this measure will be, it will look like that, right? So we just look at what is the easing measures that we already saw. It's going to look like, so we have G, if we want, we have what is called Kn, and we also have to scale beta to depend on N, and so the measure mu N beta B of X belong to minus 1, 1 to the N, right? It's an easing measure. There is a normalizing constant. And what's in the exponent? Well, I claim, let's do the calculation on the side. What should be in the exponent? There should be a sum xi, xj, ij equal 1 to n, maybe I not equal to j, but we are having a complete graph. So every pair is going to be an edge. We should scale by beta, so I'm scaling by multiplying by beta n. The reason is now we have n square edges. We want the overall contribution to be of order n, so we divide beta by n to make sure that it's going to be that size. And then we have a b times the sum of xi, I equal 1 to n. Right? So this is Hamiltonian, or this is our Hamiltonian times beta of h. Just write it like that. Usually, sometimes I put the beta outside. Here I don't. This is our Hamiltonian. But you know, this xi square is always 1, right? Xi square is always 1. So up to a constant, which I can anyway incorporate into this Zn, I can just forget this condition, right? I can just forget this condition, and it only changes by a constant. Okay, but now I'm in better shape because what I have here can be written in terms of x bar. Let me call x bar the average. Okay, let me call x bar the average, and let me rewrite what appears here in terms of x bar. And I claim that what is written here is beta over, this should be probably maybe x less than, okay, maybe something like that. Okay, it depends whether, there is a question whether you count every edge twice or once. If you want to count every edge once, you really should go over I less than j between 1 and n. And then after I remove the not equal and change it to, maybe I do that, like that. Now I change it to 1. I did a mistake. I change it to 1/2 ij equal 1. Okay. And then what I get beta over 2 x bar square plus b x bar all times n. This is just algebra. X bar is this divided by n. I multiply back by n is exactly this term. Here, if I add the diagonal terms and take half of all the terms, what I will end up with, I can write the sum of xi times xj. I can just write it as the sum of xi squared. And if I rearrange and put the beta here, I get exactly this contribution. So the end result is the Curie-Weiss can be written as follows: n beta over 2 x bar square plus bx bar. So you can see that, that the measure depends on the configuration through exactly one parameter, x bar. Every vector with the same x bar exactly has the same probability. So what we need to do, we can do large deviations for x bar. X bar cannot take too many values. And what we can write, p x bar equal to m, I claim should be approximately 1 over zn beta b times expectation of n phi of m. And what are the values that m can take? M takes the values minus n over n all the way to n over n. Right? So there are not too many values that m can take. There are about 2n over 1 possible integers divided by n. And I want to calculate what is phi of m. And I claim that phi of m is beta over 2m squared plus bm plus the relative entropy of 1 plus m over 2. And what is the relative entropy? This function will appear again. This will be a binary entropy. So not relative entropy, binary entropy. It's a function h. The binary entropy of p is going to be minus p log p minus 1 minus p log 1 minus p. P is between 0 and 1. Okay, this function, the binary entropy, looks like that. This is h of p. This is p, 0, 1. And this is 1/2, where it is equal to log of 2. It's a symmetric function around 1/2. It's maximal at 1/2. It's an entropy. Entropy is maximal when you are more or less equal. And it's equal to 0. It's 0 at 1. Now, where did I get this estimate? This quantity I simply copied from here. These two pieces I simply copied from here. Right? If x bar equal to m, I just plug it here. So where is the approximate? Well, I need to count how many binary vectors have a particular value of x bar. Right? So this really comes from the statement. This is lemma. This comes to this. Let me write it. No. Okay, so this comes from having number, the probability having the number of minus 1, 1 to the n vectors of average equal to n is about e to the n. I will call this thing I. Maybe I will call this thing I. I don't want to call it H. H too confusing. No, I'll call it H. And how do you do that? This you get by essentially, if you want, Stirling approximation to the binomial. The transformation from the average being equal to m to 1 plus m over 2 is exactly the statement that when you move from minus 1, 1 to 0, 1. And what you have here is you ask the question, what is the chance that a binomial will be equal to a particular value? So you can write it as n, choose this value, times 2 to the minus n, and you can work it out. And you put in also the 2 to the n because we actually count instead of looking at probability. And so really this calculation is an approximation of n. This is an approximation of n. Choose n plus 1 over 2. You just do Stirling approximation to all the terms that you find. Note this. This is multiplied by n. Stirling approximation to this quantity. Okay, so what do we do with this? Okay, what do we do with this? Well, we can use this nice expression now to analyze the behavior of this measure, right? First of all, it's uniform over this collection. And now we just need to see what is how this behaves. We can also find this z, right? Because there are not too many values of m. The number of m's is polynomial in n. So you can approximate. And also approximate the z and beta b. And what we will find is that this is lemma 1 point. So this is really lemma 1.2. This is lemma 1.2. This probability is a mu, so I didn't write it correctly. This probability is a probability under the Curie-Weiss model, under this model. This is called the Curie-Weiss model. So this is lemma 1.2, and then using it we can move to lemma 1.3, where we can calculate the free for all n large enough. In principle, the free energy, 1 over n log the Zn beta b, is approximately phi star beta b. And what is phi star beta b? It's a supremum of phi beta b of m over m in minus 1, 1. And this is a b we can get the free entropy by the free energy by studying this function of one variable from minus 1 to 1. Just plotting it or doing some calculus to find where the maximum is, and this will tell us where the value of phi star is, but it will not only tell us that, but we know, since we know that the distribution is uniform subject to x bar, we can figure out what are the typical components. Where is this measure going to be for very large value of n? It's going to concentrate around the value of m, x bar will concentrate around the value of m that maximizes this quantity. Okay, so this is lemma 1.3. And then we can do the calculation, and we will arrive at some conclusions. So now we do calculus. The soup obtained when phi beta b prime of n equal to 0. And this is equal, you just calculate, you just differentiate this function. It's not difficult, quadratic, linear, so it's linear, constant. You have to differentiate this entropy, but it's not very difficult. You just differentiate this function in P. It's not too bad. And when you do the algebra, it comes to be at the solution of the equation m equal tangents hyperbolic beta m plus b. Okay. So what I did, I simply jump over a step, but I calculated the derivative. So I got the beta m, I got the b, you can see, and the tangents hyperbolic come from differentiating this guy. The antiderivative of this guy will give me this. In principle, I should get beta m plus b. It's come from the fact that h1 plus x over 2 prime is arc tangents hyperbolic of x. E to the x. So if I get arc tangents hyperbolic of x, maybe x is not a good letter here. P. Q. So if you get arc tangents hyperbolic of n equal to beta n plus b, probably there is a minus somewhere. Minus. Then you arrive to this one. Okay, so now the question is to draw some pictures that show us how this thing looks, and in particular how it depends on, how does it depend on beta and b. Okay, so here is a situation. Here is 1, and here is minus 1. And in the beginning, there is going to be, if beta is small enough, there is going to be only one solution. And if beta, so if we plot the phi, beta b, in the beginning there is only one solution, maybe something like that. It's a monotone function. This is beta small. This is where the maximum is obtained. There is a unique maximizer. But then, when beta becomes large enough, essentially when beta is greater or equal to 1, you can have this situation, let's say B equal to 0, then you get complete symmetry, and you get maximizer, minimum, maximizer, minimum, everything is symmetric. So you have M star, M minus, and M0. This is a minimum and two maxima of equal height. And if you take B positive and beta still greater or equal to 1, what you will get is that the maxima at M star will go up because of the B. So this picture corresponds here. B equal to 0, beta small, or less than 1 really. This picture, and here I have the third picture, where now the first maximum is bigger, the minimum is no longer at 0, it moved to be negative, and then there is a smaller, it's not going to 0 necessarily, like that. Right? So this is my M star, this becomes my M0, this is my M. Always two maxima and one minima in between, and the largest one is always going to be the dominant one if I choose B greater or equal to 0. If I choose B opposite, the whole picture will be completely reversed. You can check that changing B, changing M by sign is exactly giving you the same solution. Because the tangent hyperbolic is an odd function. Okay, so from this, what we conclude is theorem 1.4 and 1.5 that says that if beta less equal to 1 or B positive, then for every epsilon positive and for every n large, the probability is that x bar minus m star is bigger than epsilon is less equal to 1 minus e to the minus n c of epsilon. Essentially very small. So x bar is going to be concentrated around m star, and our measure is really very close to a uniform measure on a sphere, if you want, or a piece of the hypercube, which have exactly or almost exactly or precisely around this number m star. It's like a magnetization. So we have a good description of what the Ising measure is in that case. This is equation 115 in this survey paper. But there is another case which is more interesting. If beta is positive and B is 0, bigger than 1 and B is 0, then we have a situation which is now different, because now we will concentrate around this one. Sorry, this was like that. I mistook it. I was not doing an upper bound. This is going to be at least all my directions. The difference is going to be that in this case, where I have exactly two equal symmetric maximizers, it's not true that the measure is going to concentrate around one of them, but it's going to concentrate equally around each one of them. So each one will get measured about 1/2 minus a small correction term for everybody else around us. And whereas in the other case, they're all concentrated around 1. And this brings us to the notion of coexistence. And that's the last theorem I want to show from this part before we move to the second part. Go here. Now this theorem is really easy once you did your calculus, right? I mean, this is just drawing or just checking what type of solutions this equation star can have. And I already know that my distribution is just going to be like that up to a constant, right? So if there is one point which dominates, I can calculate and the function is very nice, and I don't have too many possible points, I can just bound the probability assigned to everybody whose value is, once this guy is slightly off of n star, I can just check from this picture that the maximum height I will get will be slightly smaller. Everything here is multiplied by n, hence I will get this very small probability. On the other hand, in this case, because of symmetry, it's everything okay, except this guy takes exactly the same amount as that guy, so I'm exactly 1/2 to each. So this theorem is just an elaboration of the picture that I drew to you, or if you want, counting the number and size of solution of this nonlinear equation. And the nonlinear equation is simply just a calculus of calculating the derivative. So all that we did really was to do this calculation. That's a very simple type of large deviations. And finally, I want to say that Curie-Weiss exhibits coexistence if and only if beta is bigger than 1 and b is greater or equal to 1 and b is 0. Now I need to plot to you what coexistence means, and the best thing to show it to you is the coexistence is this picture. This is coexistence. Now, what does this picture mean? It means that there exists two sets, omega plus minus, or there exists, if you want, omega plus, which is all the x having the sum xi greater or equal to 0. And then omega minus is omega plus complement, such that the mu and beta b of omega plus minus is greater or equal. I'm just copying what I had there. And the mu and beta b of the boundary epsilon of omega plus minus is going to be. Now, what is boundary epsilon? Boundary epsilon means here I was looking at greater or equal to 0. In the other one, I would look at strictly less. And the boundary epsilon is just all the points whose distance, if you want, or the sum from n to I is going to be less than epsilon. What do I want to say? This is between. Depends how you do the boundary, but it really doesn't matter for us. If you want, you can just make it symmetric, okay? Let me just call it like that. You just go n epsilon on both sides. And this picture shows you the volume or the measure, that the Ising measure mu assigned to these sets. So these sets take a large amount. If you want, the set is up to here. This set also takes a large amount, half, but this corridor is relatively large. It has size 2 and epsilon, but it has a tiny mass, right? The mass is tiny. You should think of it like this, a bottleneck. And that's why this is called coexistence, because it suggests that the configuration split into two pieces, one corresponding to magnetization m star. Really, I could have shrunk it even more. This is magnetization m star, magnetization minus m star, and in between there is a very small probability. And this is very common to, in general, so generally expected of Ising. Generally expected of Ising, and also in principle of Potts. Just Potts may split, Potts split to Q. Right? Because Potts has a Q-fold symmetry. If you put B equal to 0, it has a Q-fold symmetry of permutations of the different colors. Ising has. So this is ferromagnetic, all ferromagnetic. Here I already took ferromagnetic. If I took anti-ferromagnetic, the situation would have been different because here I always took beta positive. I didn't say that, but I always took beta positive. If I take beta negative, it's becoming different and maybe more related to the structure of the graph than I might want to admit. And if you remember in lecture one, I described the Montanari, Mossel, Sly, and follow-up work with Basak on coexistence of Ising on tree-like, graphs. So in principle, with work, this is also proved. This coexistence picture, for example, was proved in the 80s or 90s, was proved for Ising on lattices, and more recently, a few years ago, 2010, I think, is this one, or maybe 11, I don't remember, I think 10. It was on the slides for lecture one at the end. This is maybe still waiting to be published, I don't remember, but it's posted. Was proved to tree-like graphs. Now, let me mention what makes the Curie-Weiss, now that we see the phenomenology, let me ask if there are any questions. Any questions? Okay, so this is a general principle of Ising and other ferromagnetic models, that high temperature, nothing exciting happens. Low temperature, you split to the different phases. As I said, it's supposed to hold on many situations. Why was it so easy to do it for the Curie-Weiss? It was so easy because on the complete graph, from the beginning, we could write the Hamiltonian in terms of one functional. If I could write the Hamiltonian not in terms of one function, in terms of three functional, it would not be so difficult. I would just do the calculus here over a function of three variables. The problem why I cannot do such easy calculation on a lattice or on tree-like graphs is because once the graph is far from the complete graph, it is no longer true that the measure is almost uniform except for few parameters, and I can just do the calculus on few parameters. Specifically, I also cannot do this kind of large deviation analysis where I get so nice so nice bounds because I'm not directly doing that. I'm using different schemes. So, for example, in this case, the idea is to look at the possible measures on the tree. That's what we discussed in lecture 3. And the measures on the tree were corresponding to free measure, the free corresponding to M0, plus measure corresponding to M star, and minus measure corresponding to M minus. And you saw why, indeed, somehow the M minus and M plus are playing a role, but once you put the positive magnetic field, somehow the M minus is removed, and on the graph you can just go from, if you want, from here to here, and that was where we had the monotonicity and so on that helped us in lecture 3. So the tools are very different. So in general, statistical physicists will consider the problem trivial if you can do it using large deviations. Rightly so. However, if you can do it using large deviation, you get the best possible result, right? You got yourself the exponential tail, you understand exactly where everything is, you can do even finer asymptotic, so you are really in control of getting anything you want out of this problem. And generally, you will even be able to do large deviations, usually even in cases where are more complicated, not on the complete graph, if the beta parameter is very small. But if the beta parameter is large and you are having more involved calculations, like in the spin glass models or in sparse graphs or on lattices, large deviations usually goes down the tube. And you have to use some other tools. It's just asking for too much that you cannot get. Okay, so this was an easy calculation but to give us a feeling what we would expect from ferromagnetic models in terms not only the, and notice another thing is that we really aimed at calculating the partition function, but there was a principle, right? If the partition function can be written as a variational problem, then figuring out who maximizes a variational problem usually will tell you where the measure concentrates, which is really what you wanted. You never wanted to calculate, who wants to calculate normalization constant, just to calculate normalization constant? The whole point why physicists are insisting on calculating them, because there are all sorts of parameters in, and they expect to get a variational problem, and they expect that the solution of a variational problem will tell them where the measure is in the limit, which is what you really want to know. And that's exactly what happened here, and that's exactly what we kind of did in lecture 3 for the problem with for calculating the beta prediction, except there we knew how to do maybe this part, but we really didn't know how to do this part, because we really did not have large deviation. We were calculating this thing somehow in a kind of roundabout approach, so it did not give us anything except the normalization course. But it gave us supporting evidence where to look the support of the measure. Any questions before I go to the second topic? Not for easing. Not for ferromagnetic easing or pots. So they are still adhering to this picture. That's ferromagnetic models tend to be simple, because if you want, in a ferromagnetic model, you know what the ground state is before you start. That's what I said. You can actually solve the beta equal infinity easily, because the maximizing configuration is kind of obvious from the start. Whereas in the cases where there are frustrations and conflicts, it becomes harder and harder for people to decide what to do, not to draw on any recent events. And as a result, it's complicated. And somewhat unexpected too. Okay. So now I want to go to another topic, which shares that we are going to do again large deviations, kind of large deviations. The difference will be that this large deviation that we did here was relatively easy. It fits a framework of Varadhan's theorem, Varadhan's theory, if you want, Varadhan's theory, or classical large deviations. You can call what we did here large deviation principle, and so on and so forth. And derivation was very similar to the standard way, except it was so elementary it didn't need to do much, because everything was discrete and I could do binomial approximation. But in principle, what I did, I expressed the measure in terms of some approximate statistics and broke it into not exponentially large number of possibilities for which I have a good approximation, and I did the normalization constant as a soup, something called Varadhan's lemma. In contrast, the next thing which I will do is also going to be a large deviation analysis, but it will not adhere to this technique. That's what I said, it's a nonlinear large deviation analysis. It also is applicable for problems on sparse graphs, let's say Erdos-Renyi graphs, but it is not necessarily about statistical physics. Actually, it's not about statistical physics. The motivation and the type of result. Nonlinear large deviations. So what do we want to solve here? We have a function a real valued function, which is twice continuous differentiable in the boundary of our set, with derivatives extending continuously to the boundary. It's a function on which we can do calculus. And we define partial derivatives. They just will appear a lot of things. So let me just use short notations. Fi is the first partial derivative, the vector of gradients. Fij is the second partial derivative, vector. And suppose we have some control on them. Suppose we have on various terms. A, which is a subnorm of F, Bi, which is a subnorm of Fi, and Cij, which is a subnorm of Fij. And I will call this smoothness. Meaning at the end of the day, when I write a theorem, in a theorem will appear all sorts of A's, B's, and C's, and N's, and I hope that whatever appears in the theorem is going to be small. So let's assume that all of these terms are not too big. As well, we also have another information on the complexity of the gradient vector. Right, the gradient vector is simply this vector Fi for the corners. For x, 0, 1 to z. And what is the complexity? What is this complexity? It means that for every epsilon, there exists some set d epsilon, a finite subset of vectors in Rn, which is sub-exponential size. This is sub-exponential size, or if you want, the 1 over n log of the size of d epsilon, which d epsilon depends on n here, is going to be small, such that it's a good approximation of the gradient vector. What does it mean? For every x on the corner, for every corner point, I can find some vector d1 to dn. This is a vector in my approximating set, such that the error in L2 between Fi of x and di is less equal to epsilon squared. So this is the setting. Again, I have a function that has two properties. Property number one, I have control on the function up to second derivative, maybe uniform control. And property number two, on the corners of the cube, I can, if I write the gradient on the corner, I have 2 to the n different gradients. So the whole game is, of course, if you let me use d epsilon whose size is 2 to the n, I will be trivially done because I will just choose for d epsilon these vectors. There are only 2 to the n vectors to consider. I will just put all of them in there and get 0 error. I claim that for even, I'm assuming that this function, somehow this gradient function is not too complicated in the sense that I can approximate it by much less than 2 to the n different vectors. Somehow there are many x's, 2 to the n different x's here, but maybe the gradient doesn't take too many values, or almost doesn't take too many values, or many values of the gradient are too close to each other, I can replace them by one vector d. Okay, now what do I want to do? I want to approximate some quantity which involves the value of the function on the corners. So our goal is to approximate, so I'm going to talk about theorem 1.6. We want to approximate, and this is theorem 1.6 in my paper with Shurav, and it is also theorem, I think it's 10, is there a 10.1 or 10.2? Shurav survey paper, I think 2. One, not interesting. For those people who take the notes, let me just write, no, 10.1. 1, chapter 60. Okay, so what do we want to approximate? We want to approximate something that looks like a partition function, but without the normalization. F, which is a log of the sum over x in the corner e to the f of x. And how do we want to approximate it? And I'm just going to tell you how I'm going to approximate it. As f star, which is a sup over x from 0, 1 to the n, f of x minus I of x plus lower order terms, which are complexity plus smoothness. These complexity terms will involve d epsilon. They involve really n epsilon and the log of d epsilon. Involve n epsilon log d epsilon. And these smoothness will involve a di Cij. And I did not say what is I of x. I of x is, or I of u, right, I of u is the sum, I of x is the sum of I of xi. It's a bit bad notation, maybe I should call it like that, I like this, so it will become clear. These two lines, right? This is a vector. Here, okay, this is a vector. And what is I of xi? I of u is minus h of u of the previous story. So it's minus u log u, minus 1 minus u, plus really. Might have made a mistake in the sign somewhere. Let me just check before I try to prove it. Just check that I don't have a typo. I always have typos with this sign. I is with a, if I is with a plus, you put a minus. So if I is with a plus, then you put minus. Good. Okay, so I did not make it. Yes.
When you say log of d epsilon is like a subset. It's
Sorry? If I take?
D of epsilon is a subset?
A size. Okay, so let's see what we are trying to do. So the goal is pretty ambitious, right? So we take any function on the corners of the cube, any function, right? Looks like that. I mean, if we can succeed. And then we will try to calculate this log of the sum. Why do we want to approximate? It's kind of obvious. There are 2 to the n different terms in this sum. It's very difficult to calculate such a sum. Right? It's exactly, it's more general than all the, if we can solve this problem, we can solve all the problem of statistical physics as a special case. Okay, so it's quite ambitious. Of course, not all f we can always write something like that. I will write you always something like that, but often these terms will be bigger than this term, right? Kind of the statement of the theorem says, my error is smaller than my main term. If not, fail. Now, this is a very interesting approximation. It looks exactly like what we did in the Curie-Weiss. It's a classical large deviation approximation. Look, just put here f of x and assign to each x approximate probability e to the minus I of x. And then just take the maximum instead of taking the log of the sum. Now, the problem with this argument is twofold. One, we cannot do it individually on each one. Two, notice that we also moved from the corners into the inside. But in the original problem here, the value of f inside was never specified. So you can imagine giving me a function on the corners, and I decide what to do inside. Now, if I can decide what to do inside, I can make big changes to this guy. Now, where are my hands kind of forced? My hands are kind of forced. I can even make my gradient at the corner close to 0 by simply not doing too much in the corner. But it's this second derivative that means that I must meet my, meet your maker at some point, right? I can cheat on the corners, on all the corners, but at some point you will catch me. If the function is very complicated, I try to go with 0 gradients, at some point I will need to take a big second derivative to match all these directions. So if I need to keep the smoothness honest, then I cannot cheat too much inside, and then this condition on having a small gradient is meaningful, because the gradient is really not on the point. The gradient is including the directions inside. And then, of course, the question number one is, how do you get such a theorem? And specifically, what do you stick here? Right? More precisely, what is going to sit here? And secondly, well, you want a theorem that at least has few applications. Of course, I can put here 2n, or something like that, and 2a, and then the theorem will always work, but it will all be completely useless because this has no chance of being bigger than my error term. Okay, any questions?
So if you have two boundary values of f at 0 and 1, you can always make linear interpolation. Is it better to make other interpolation?
You can make, but not on n direct, not on. You need to meet your. You come on all the core. It's not a linear. The whole point here is dimension n goes to infinity. The whole issue is when n goes to infinity. This is not an interesting theorem in 4 dimensions, in any finite number of dimensions. The goal is, really the goal is this f should grow. I didn't divide by n because sometimes this is not even growing like n, but some other function of n. But this is supposed to grow with n. You supposed to capture here the leading term as a function of n, and you hope that these things will be smaller as a function of n. And I will give examples where this was done.
So your goal is also to find a good, interpolation of f inside.
That is true. The good point of Ryuk is that in principle you gave me only f at the boundary, and there are many different ways to extend it inside, except that in the examples we know somehow f comes very naturally. If f is like a sum of xi, xj, you would expect to just do it also inside. Why put something strange inside? So usually, in many of the examples I know of, the f somehow comes already in a natural form, meaning it's on the corner, but it comes with such a small, nice formula that you are tempted to use exactly this one. But it's right that maybe there are some other less trivial extensions which will do better.
So what kind of example do you have in mind? I'm sure you will explain later.
I did not explain anything yet. You are sure that I will explain? I'm hoping that I will explain, but it's a good idea that I will explain the examples maybe, because then there is a chance that I will not get to the proof. Not a chance that I will not get to the explaining the examples. Maybe, okay. So let me explain the examples. That's a good idea. Okay, so first, let me write here application with quotation mark, because application with quotation mark is not really an application, but it is theorem 1.1 in our paper. And this is as follows. You have Y, which is Bernoulli. Bernoulli P IID, and you want to check that the log of P of G of Y greater or equal to Tn is approximately phi P minus phi P of T minus delta and in principle, this complexity and smoothness term will be a replica of the complexity and smoothness terms that come here, but there are just going to be more of them. But how do I connect this problem to the previous problem? The difference is here I no longer, here I did some calculation of a log of a sum, and here I'm doing a log of a probability for Bernoulli random variables. Now, my Bernoulli random variables do not mean that this is not a difficult problem, because it's a very complicated function of the y1 to yn. So the fact that they are Bernoulli is great, but I cannot do very much with it. And what is a phi p? What is phi p of t? What do you expect? So it's again, it's this kind of Varadan principle. What you are going to do, you are going to take the minimum of IPX over all possible x in the inside of the cube, such that g of x is greater or equal to Tn, and IP of x is the sum I equal 1 to n IP of xi and IP of u is a binary entropy, relative entropy between two Bernoullis. This function is also called in the large aviation literature the relative entropy. There should be a, yeah, there is a minus, which is non-negative and is minimal. This is just a comment, minimal, 0 when u is equal to p. It's like a measure of difference between two different Bernoullis, Bernoulli u and Bernoulli p. This is your reference measure. Think of changing the Bernoullis here to new Bernoullis. This quantity is exactly calculating the rate function. That is, what is the cost of changing all these Bernoullis p to different Bernoullis xi, maybe not the same I, maybe not the same parameter. And what you are doing, you're taking overall, you take the change among all the possibilities that exceeds the threshold, you are going to take the one that has the least cost of changing these Bernoullis to these parameters. That is a principle of large aviations, and we hope that our problem G here, that the function G is such that these complexity and smoothness terms are not going to be smaller than the leading term, which is what we would expect to have. And this delta is simply giving us some room to massage the problem a little bit. Now, what is the connection between this? So I will actually prove to you, the upper bound, because the upper bound is a challenging part, not the lower bound. You almost kind of saw how I achieve the lower bound. I'm simply changing my Bernoullis to Bernoullis xi. This is exactly the Radon-Nikodym derivative, what is written here. And I just choose the one which does the job. And then I pay the cost, and that's what I get. So the lower bound, I don't even need all these terms. But in the upper bound, I'm going to go through a procedure. I will invent a smooth function f of x, which is...
Meaning you can choose delta as small as you want by changing the error.
for the lower bound.
I mean, I'm asking what's the statement.
The statement is not written. There will be some smoothness and complexity terms, and they will involve a delta in them. And they will involve an epsilon in them. And the epsilon will depend on the delta and will come from these smoothness and complexity terms. I'm just trying to check how you get from this theorem to this theorem, and then I will give this finally the answer to Takashi's question, what are the real applications? I am going there. But this is a general principle also important in large deviations. You simply approximate the indicator by a function which is 1, or e to the minus m. M is very large. And in our case, you need it to be smooth. So you find a smooth function f, which is 0 if g is greater or equal to Tn, and is minus fm if gx is less than t minus delta n. Hence, hence here is my problem. I need it to be smooth. I cannot jump. And apply theorem 1.6. And so whatever sits here will be whatever comes from here. So if you want, this is my function. Now let's write what my function e to the f is going to be. Well, my function e to the f will be 1. This is g. If I exceed Tn, it will be very small number, e to the minus mn. You can make it small enough that it will not bother you if you are below t minus delta n, and then you do something here in between. And the something you do in between, you are trying to shrink this as possible, like Ryoki wants me to do, but you are trying to make the first and second derivative to be as least harmful to you as I want to do, and you want to make this guy very small so it will not bother your calculation of the indicator. And obviously all these three goals are conflicting to each other somehow, so you massage it so it will work. This is actually delta prime, I think. Delta prime is not exactly equal to delta. I don't remember why, but it doesn't really, not that important. So the point is, and this is a classical strategy in large deviations, is there is also a similar classical strategy in proving central limit theorem or weak convergence, which is, it's much better to work with continuous or differentiable functions than working with indicators. So in case of need, you replace indicators by smooth functions that approximate them. And that's what we do. In a central limit theorem, usually you take nice bump functions and prove some limit result for them. That's essentially Lindenberg method to prove the classical central limit theorem. The difficulty in large deviation is that you need this to be 1, but you need this to be extremely close to 0, and you want this to be relatively small, and you don't want to pay a lot, so it's much more tricky, which is why the smoothness, and if you read this paper, you will see that the smoothness and complexity terms here resemble those here, but they are even much uglier. And that's why there is no point in going over the proof of this theorem, because it simply sends you to the other one anyway. Okay, now come real applications. Right? Okay, so the real applications I have are two classes of applications. One, and I will go over mostly on one, which is counting subgraphs of a sparse graph, random graph. Random sparse Erdos-Renyi graph, counting how many graphs have a certain number of subgraphs. Specifically, so you want to count, we want to count the number of sparse graphs. But counting the number is the same as counting the, if you want, is exactly the same as counting the probability. Sparse graphs, and here it will be G, which is Erdos-Renyi G n Pn. where Pn goes to 0, not too fast. And if I want to be honest, I will say almost embarrassingly slow is an honest way of saying not too fast, because it's going to be much slower than needed. But which kind of sparse graphs? Having a certain unusually high number of subgraphs, subgraph H counts. And most importantly, find, or alternatively, if you want, find the large deviation rate function for it. Here is an example, and this is theorem 1.4 of the same paper. Also, you can find it in Shurav's survey paper. X greater equal U X minus psi PU 1 plus little order in 1, and n goes to infinity. This function is explicit function, nice short function depending on what is x. And x here specifically x is t h g, and u is bigger than 1. Okay, so what do I need in order to explain what happens here? Okay, so I need to explain, I'm not going to explain this, it's written in the paper. It's really an application of this thing. The specific problem at hand. What is this thing? I explained. It's just some number, some rate, which goes to n to infinity. The Pn is the probability of my Erdo Shreni. It should go to 0, not too fast. And what is THG? THG is a number of appearances of H within G. Example. If I take H to be, let me, off there. Actually, I don't need this probably. I'm going to erase it. Any questions about this application before it disappears? No? Okay. So let me explain what example of THG. So if you take H to be this, then THG is the size of EG. You count how many edges you find in your graph. If H is this picture, then THG is a number of triangles within G. So what's the point here? You take an Erdo-Shreni graph of a large size n, and you ask, what is the chance that such an Erdo-Shreni graph will produce a number of edges? That's trivial, actually. This is the only case which is really trivial, because the number of edges is IID. It's the sum of IID. This is just binomial. You don't need my help there. This one is harder, because the triangles, this triangle involves 3 edges, and they are different triangles sharing the same edges. So you're asking, what is the chance that we have an Erdos-Renyi graph with a particular parameter Pn that has a bigger than usual, that's this U bigger than 1. We do this large deviation only in one side. We don't know how to do the other side. It's very different strategies and proofs. What's the chance that for large N, the number will exceed its mean by a factor, 2 or 1.1? Now, people have before did this calculation in the sense that they know the rate in which this goes to 0, but here you get the explicit rate function, the constant in front. You don't get correction term, but you get the constant in front. What is easy to do in these cases, it is easy to compute the expectation of x, right? It's an example. If H is triangle, it's going to be n choose 3 times P and Q, right? Very easy to do that. You count how many triangles can be there, and you calculate the probability that each one of them will be 1, will be there, right? The edges are independent. Each triangle involves 3 edges. There are n choose 3 ways to choose 3 out of n. You can do that. It's not so difficult, actually pretty easy. Pretty easy to do law of large numbers, meaning to check that x over E of x converge to 1 when n goes to infinity. It's harder but possible to do central limit theorem. Possible to do central limit theorem. Of course, in order to do that, you start wanting, for this, of course, you want E of x already to go to infinity. You cannot do a law of large numbers or central limit theorem where the actual expected number is half, because the random variable is integer. And for central limit theorem, it's even harder. But it's possible to do central limit theorem, and the trick is to use Chen-Stein method. It's worked like beautifully. You have here a sum of indicators, right? Lots of them. And you can use a method to do Poisson approximation. There are, of course, overlaps, but there are not too many overlaps, so this will work very well, give you a Poisson approximation. Poisson with a large parameter, lambda n, let's call it lambda n. Poisson with a large parameter can be normalized to become normal. No problem. The trick is not to use methods which are geared towards time series, because there is no time series here. Because they are not organized on the line. It is also possible, but even harder, to get the right tail. The right tail. This was done about 10 years ago. 10 years ago. By Chatterjee, among others. And Johnson. A few other people. Wu and Kim, I think. Kim and Wu. This was kind of the rage in the, maybe more even, about 10 years ago, slightly more, 10 plus years ago. And then the question was how to do the large deviations. And this was done more recently, after all of these things, by Chatterjee and Varadhan when P was constant. Chatterjee and Varadhan did a large deviation when P is P, bounded below. When P is constant, there is a theory developed in the last 10 years by Lovac and other people of graph limit. You can use this theory, combine it with classical tools of large deviations, and together they give you a very satisfactory result in the sense that they give you the rate functions, the one you would expect, the one that was predicted before. I made a conjecture. When Shurov was a PhD student, I made a conjecture and told him that this is his goal to solve before he left Stanford. He left Stanford, went to Berkeley, went to MIT, went to Cornell, to Courant, met Varadhan, and together they managed to solve my exercise. I was very proud. So the moral is always give good exercises to students, one they can carry with them for many years, and if they are successful, they will solve it for you. So anyway, but the sparse graphs is even harder. because the classical methods of large deviations are never going to touch it. And the reason is that for the principle of Shura-Varadhan, Chatterjee-Varadhan, was based, as I said, on graph limits or on graphon theory. Graphon or graph limit. And graphon of graph limit is based on Semeradi regularity theorem. And Semeradi regularity theorem, when you try to do it on sparse graphs, completely drops dead on you, really. So you can do something, but it's so poor quantitatively that nothing will recover from that. So you need a different idea. It's not going to work this way, even though the formula that you expect at the end is very similar to the formula, as you saw, is a classical form. I erased it, but the classical formula of large deviation coming from here. It just says, look, just do what you would have done if you were very naive. Physicists call this a naive mean field approximation. Why naive? Not that it's naive to prove it, not that it's naive that it holds, but it's the first thing you will try to do if you're looking for a simple answer. You said, well, I will replace this by taking probability to each element and then replace the sum and the log by the maximum. That's kind of the simplest variational problem. The variational problem doesn't appear anything that you wouldn't expect. No Parisi formula, no PDE, no object that was not there already on the problem. Okay, let's do a break, and I will go over the essence of the proof let me say one more thing. Okay, let me say one more thing, and then we have a break. One more thing, two. This theorem, if you want, combination of Chatterjee-Dembo theorem 1.4 plus analysis of psi pn u I Bhattacharya, Ganguly, Lubetsky, and Zhao is what gives you the right answer. So what we get eventually is a rate function, but if you remember, the rate function involves a sum over n terms. What Bhattacharya, Ganguly, Lubetsky, and Zhao did, they used the graphon limit theory as a tool to help them analyze the rate function and found a very simple explicit formula for this psi. So we have explicit, they have simple explicit, which is much better, like a one line. Now, the reason this is very good is because this is also telling you, as we said, this variational problem or the maximizer tell you roughly how you would expect the sparse graph to look. Because they are using analysis on our calculation, if you want, of normalization term, we are at the same position that I mentioned about in lecture 3, that we don't really know how to prove that conditional on being such the graph would look like that. We believe that strongly, but we cannot prove it. That is one. And two, another application is the same principle for counting arithmetic progression. Counting arithmetic progressions of fixed lengths K in a random Bernoulli subset of Z minus NZ. So you take the integer modulo n, so it gives you a nice circle, large circle. You choose a subset randomly, Bernoulli, sparse set, so Pn is the probability of choosing an element there. You get a sparse set. Now the question is how many arithmetic progression of length 3 you can find there. You can see that this is also a very difficult, even more difficult Bernoulli function, Boolean function or Bernoulli function, counting function, but it's the same analysis. This arithmetic progression adhere to the same principle. Of course, in the second step, it's no longer analysis of graphs, but it's now using Gauer's powers to get this thing. In our paper, we just find the same principle and we don't analyze the rate function. But Acharya and Sri Ganguly and 2 other people Acharya, Ganguly, Zhao, and 1 person replacing Lubetsky did this analysis using Gauer's powers. So you need now to use arithmetic combinatorics, number theory and stuff like that, because it's a different function. But the first step is coming from a different theorem in our paper, different application. Okay, so now a break finally, and we will continue at 4 for whatever. Section 10 of chapter 16, and the applications that I did before were taken from the introduction, chapter 1 here, and I think in chapter 16 it's maybe chapter 8 or 9, because the first 7 chapters are about the dense case, which I skipped completely, the chapter G. Okay, so let me go over the proof of the upper bound, because the proof of the lower bound is really easy. I don't think I have time for both of them, so if you want to read the proof of the lower bound, you can read it yourself. It's really almost done by very easy. Okay, so what we are going to do, first we are going to define a random vector x, which has an element is a random vector 0, 1.
You need to use my.
Oh my God, so I forgot my. Yes, I forgot my. I forgot this one. So the proof of we will go over the proof of the upper bound, and we will start by defining a vector x, which is a random vectors on 0, 1 to the n, which is distributed according to our target function. Okay, so it's actually having a PDF. This is a finite. This is just a finite space, so it's nothing fancy about that. So we have the distribution function of this is exactly that. The e to the minus f normalize it exactly to the total mass 1. Exactly the same as partition function. Okay. That is number 1 item. Number 2 item, we will define now x hat I of x as we go over x on the cube. Right? And it is given as follows. It's an expectation of this random variable xi, condition on knowing all the other variables. So you give me a configuration on the cube. I throw out one element, and I replace it by the value of the expected value of this vector, this coordinate, when I use this distribution. So let me write to you what this is. This is going to be e to the f x I 1 divided by e to the f x I 1 plus e to the f x I 0. And you can guess what my, maybe I should write it opposite actually. I wanted to write it like that. 0i and 1i. This is 1. And what do I mean by x1i? Well, x1i is x1 up to xi minus 1, 1, xi plus 1. It's a vector where I replace one coordinate. I'm given a vector here. I just replace one coordinate by either 0 or 1, and I check what is the mass of this divided by the sum. That's exactly what I get from this guy. I can also write it, if I want, as 1 over 1 plus e to the minus delta I fx. And you can guess what delta I fx is. Delta I fx is the f of x 1, 1 here, 1 or 0. Now I forgot which one. Minus, it's probably 1. Right, take this. Yeah, 1 minus f 0. This is kind of like discrete approximation for the ice gradient. And I change from 1 to 0, and I will call this function u of delta I of x. And what do we know about u? We know that u delta I of f, no matter what x you put there, is a function between 0 and 1, right? It's 1 over 1 plus something. And you can even easily calculate the derivative of u and see that it's less equal to a 4. So it's not a bad function. Okay, and we are still not done. This is just preparing all sorts of notation. We will define the vector x hat, and the vector x hat simply collects the x hat 1, x hat 2, up to x hat n. So what is x hat doing? It is mapping the corner of the cube to the inside of the cube. That is probably going to be a big element of our calculation, right? Remember that in the f star, we should go somehow from the corner to the inside. That's the way we go from the corner to the inside. We use these conditional expectations to find an inner point. Okay, now comes plane number 1, which is kind of the crucial element of the whole proof. There are really two planes which are the crucial element of the whole proof. One which is difficult, which is 1, and 2 which is easy, which is 2. In plane 1 is when we collect all the error terms. Really. So what my goal is to do now is to replace what appears in f star to somehow try to get between f and f star. So try to approximate this f in terms of certain things. This f and this I in terms of something involving the f star. Claim 1 that with high probability x belong to a good set A. And what characterizes a good set A? The good set A has two properties, where f of x is not too far from f of x hat of x. That is property A. So this move from x to x hat, I never say that x hat is very close to x. This is not true. But I said that somehow the choice in this f here is making the value of f of x hat not too far from f of x. The target function is not changed too much. And property B is that the function g of x hat, again x hat of x, which is also I of x hat, is not too far from g of x hat of x. And all my error terms are going to sit in these two wiggles. This is where I collect my complexity, my smoothness terms. This is where smoothness will come. Now, I did not yet define those g's, and here is g of x, y is going to be the sum from I equal 1 to n xi log yi plus 1 minus xi log 1 minus 1. And you can see, first you can see two things about g, which are important to know. One, what I just wrote, the g of x hat is I of x hat, because when you plug x equal to y, that was exactly the definition of I. So if you want, doing f minus I in this approximation is exactly the same as managing to move to f of x hat of x minus g of x hat of x. And the second thing, why did I like this second approximation, is because this g is a complicated function of y, but it's a linear function of x. An exponential of linear functions I can sum even over the hypercube. Easily. Almost easily. Okay, so this is claim 1, and I will probably not get to prove it, but maybe, we'll see. Then, okay, by definition of A, we have that the sum e to the f of x, x on A, divided to e to the f, is approximately 1. Because that's exactly this. What is this high probability x is equal to A? What is the probability of x equal to A? It's exactly this quantity. Because remember how x was chosen. X was chosen according to this distribution function. So being in A means what? Means summing this over A. This means that. So the conclusion of this is, so let me write what I conclude after this lemma. First of all, f is a log of the sum over 0, 1 to the n e to the f of x. By what I wrote here, I can do the sum only over A. It's approximately the log of the sum e to the f of x over x. Okay? But then, because of A and B, I can replace the f of x by this quantity, and I can also add the difference between these two because it's very close to 0. So I can write log of the sum over x and A of e to the psi x I will call f hat. And what is psi? Psi of xy. Psi of xy is f of y minus I of y plus g of x. Again, the y was the second argument, not the one on which I sum. This approximation. Here is f of y, came from here, replacing that. And then I took this difference. I took the difference in this one and that one. I replaced this one by that one. So it's I of y, and I have gx. And I need only to sum it over x. Now, the point is that if you notice, this is a piecewise, this is approximately piecewise linear, it's a piecewise linear approximation of f of x. Why it is not linear but piecewise linear? Because different x values might give me different x hat. But if there is only one x hat, it will be a linear approximation, because the function is linear. If there are two, well, it's going to be only two pieces. If there aren't too many pieces, I can control what I do. Now comes the next step, where I actually want to use the p epsilon in order to control, to use a complexity now, to control the number of terms that I need to consider in this linear approximation scheme. So that's step 2. I didn't say, but that was step 1. That was step 1. That was step 1. Name 1, blah, blah, blah. And now step 1. So step 1 was to replace big F by F hat. And step 2 to work on F hat using the complexity. So using the set P epsilon, we will produce another set. D hat of epsilon of the same size. That's good, not too big. Of vectors, P, vectors P in 0, 1, Z, such that for every x on the corner, we can find a P in the new set, where the x hat I of x minus the pi is less than epsilon squared. Now, if you want to guess what will be the pi is going to be the u of the di. Remember, we have this function u, and what sits here is a gradient, a discrete approximation of the gradient. So what I'm doing, I have a good approximation d of the gradient. This is an integral over the gradient. The function is a nice derivative, it's a Lipschitz, it's bounded, everything is nice. So I will just push my approximant through this function and use them to try to approximate these results, which are u of the delta f. It's not very difficult to do. This is actually a relatively simple step. These guys are, as I said, are approximation of the gradient of f. Now you can worry that when you do this discrete gradient, you go through the inside, but because of the smoothness, the control on the boundary should transfer with some a bit more smoothness to the control on the inside. Because the gradient doesn't change too much if you have control on the second derivative. Okay, so now let us define P of P to be the set of x in 0 to the n such that, you know, x hat of x is nearly, and this will be for every p in our approximation. So instead of going over the cube, I'm supposed to go over the corners of the cube, if you remember, right? I'm supposed to go over the corners of the cube, the subset of the corner cube. So instead, what I'm going to do, I'm going to go over my not too many approximants to these values, and for every approximate, I will sum over all the x's, which give me x hat, which is nearly p. That's the idea. Okay, so now, I'm ready to do another bound by replacing my f hat with a more bigger one. Okay, so f hat is going to be less equal to the log. I will sum over all the p in this epsilon. I will sum over all the x in p of p. And I will put here e to the f. Let me write now explicitly what my psi was. I just replace the psi that was sitting here. I just replace the psi that was sitting here by the explicit value of psi. The three terms, and wrote the x up inside. And I also forgot completely about the a. It's just going to make it bigger. I mean upper bound. So just sum over everybody. And I break my sum into two groups. And I'm going to do this sum inside sum first. So, as I mentioned, using the approximation, well, since under this condition here, x hat is close to p, I will write f of p minus I of p plus g of x. And now you see the p will go out, this will go out, this piece will go out of my calculation. This piece will go out of my calculation, and I will be left by the sum over x in pp of this side. And I claim that the sum over x even on all of 0, 1 of e to the g xp, that is claim 2, which is actually crucial but very simple, is 1. That is the beauty of linear functions. That's exactly why I did all this manipulation to arrive into a linear function here. That was the whole point in the whole calculation, really. At some point I get to something that I can sum over the unit cube. If there was another function you can sum over the unit cube, then you can do better approximations. Now, given claim 2, you can keep bounding it. And what would you get? You will get the log. I will just replace this sum by the overall sum. This is a subset of the now I don't care. This was serving the goal of simplifying. Once you simplify, I take the larger set, and I get only 1. So I get the log of the sum over p in d prime epsilon e to the f p minus I of p. But this is going to be less equal to the log of d prime epsilon in size, just a number, plus f star. I just replace this second term. I took the maximum value here, which I called f star, took it out of the sum in the log, and just was left with how many terms I have, which is this quantity. And I assume that this is small, right? This is my main complexity term. So as soon as this log of the d epsilon is smaller than f star, I might be in business. I would be in business, except I collected all sorts of things in all my wiggles. Where did I collect things? I collected things here, and one more time. This I did not really collect another one because it was the first one, but I think I collected one more. I didn't collect much, but maybe there was a changes. No, I didn't collect anything else. So I collected all my smoothness terms in claim 1, and I had to add to pay this cost in claim 2. After claim 2 at the end. Okay, so what is left is to prove claim 2 and to write to you the theorem. And of course, I did not prove claim 1, but it's not it's an exercise in certain exercise in calculus. Now, before I do that, let me point out to you one of the strengths and the weaknesses of this method. The strength of this method is we never really ask too much about the function. Did you see anything specific about the function? No, you didn't. So we kind of fly blind. We don't care what the function is. We do this piecewise linear approximation. If it works, we are very happy. What is the negative part about this approach is what I just said is a positive part about this approach. Since we don't ask too much about the function, it's possible that we give a lot, that we shouldn't because we don't care what the function is. Now, where is the main limitation of the problem? One of the main limitations is that we insist on getting at the end to a linear function of x. So no matter what function you started here, we try to get at the end to a linear function. This kind of limits the way we can approximate things. And why do we want linear function? Because the linear function is the only function that I can calculate on the cube. If you find another class of functions, good class of functions with parameters that you can sum over the cube, then you should quickly read this paper and write another paper before anybody does. Because you are surely going to do it slightly better if you have a bigger general, more general. As I mentioned, at the end of the day, we can probably, I believe that in most cases where the answer is that this approximation F star works, this method will produce it. But it will not necessarily produce it for sets as sparse as it should do. Because here and there you give away a lot. It's like using some wrong Cauchy-Schwarz in the middle of your proof, and you give something. And then, yeah, you got something, but you didn't get the optimal thing. So one of my students tried very hard to do it under optimal conditions. But, he proved what we did, but could not get the best thing, so it's probably quite difficult to do. He's a very good student, so it's quite difficult. Otherwise, it's not necessary. He succeeded doing other things, which are hard. Okay, we also tried. I would not want to say about myself, but Shurav is very good. Okay, so let me just proof of claim 2. And you will read the proof of claim 1 if you want from both of these papers. It is, especially in the paper we wrote, it's certainly written. Okay, so just proof of claim 2 is very easy. Let's just do it. So what are we doing? Let me write what G is. Here is G. I'm just going to sum xi log yi. Okay, that's what I wanted to do, right? Okay, that's really easy. What do we have here? Is a sum over x, which is 0, 1, to the end of, I'm just going to write what is written here. It is going to be written a product from I equal 1 to n, yi to the x, yi to the xi, 1 minus 1 minus x. What you recognize is that this is just the probability of independent Bernoulli yi equal to the vector x. If you sum over all possible vectors, the product of Bernoulli obviously will get 1. I think it's a very nice way to finish the talk. On a high note. Something with no wiggles, and why I wrote P? Because I copied from here. Right. I actually looked at my notes, there is a P there. I was wondering what the P is. I was quiet. I didn't say I want to say anything. What is this P? I will give my notes to the people who take the notes, so hopefully, and they also have the references, so hopefully at the end you will get a slightly better version than what you got here. Let me just mention one word about how to do the lower bound, which I said is really easy. In the lower bound, you simply do a Radon-Nikodym type T. You already see from here what is kind of the principle here. And so you do a Radon-Nikodym theorem, and you replace F by F minus G plus G, and you use some Jensen, and you get the lower bound. It's a two-line. And you collect very few terms. Most of the terms you collected because, you know, you have to do this approximation.
Thank you very much. Other questions? Okay, so if not, the last